Biosystems at Northwestern University. He did his PhD from CMU and BS from Princeton in electrical engineering. His research interests include motion planning and control for dynamic robotic systems, robotic manipulation and under-actuated systems, assembly and automation, decentralized control of multi-robot systems, and physical human-robot interaction. Kevin has many research and teaching awards. I can vouch for the teaching myself because I remember almost 10 years back, I attended a summer school and Kevin in Kanazawa, Japan. And Kevin was, it was amazing. Incidentally, Kevin is a co-author of 3 textbooks on robotics and mechatronics, including modern robotics, which I also use as a textbook for my class that I'm teaching at Cornell now. And he's the editor-in-chief of the IEEE Transactions in Robotics as well. So Kevin, the floor is yours. Thank you again for coming.
Thanks very much for that kind introduction, and thank you for organizing a workshop that was well worth getting out of bed for at 2 in the morning. I've thoroughly enjoyed all the talks. Thank you for having me here today. Today I'm going to talk a little bit about our work on tactile sensing and the new fingertip that we developed for manipulation while tactile sensing. But I just want to start by providing an overview of the Center for Robotics and Biosystems. We're a relatively new entity at Northwestern, and we're a group of several faculty that work in different areas like bioinspiration and neuromechanics, a lot of work in human machine systems and prosthetics and rehabilitation robotics, swarm robotics and decentralized computation, and then sort of everything else falls into general autonomous robotics, and that's where today's talk will land. These are the people that I work with. Some I work with directly on topics like this, and others I've certainly benefited from working with indirectly. Brenna, Ed, Matt, Mitra, Malcolm, Todd, Michael, John, Mike, and our newest member, Ryan Truby, who just joined us earlier this month, and Paul Umbenhauer, make it a lot of fun to work together in the center. So our center spans several departments and our medical school, and also the Shirley Ryan Ability Lab, which is the nation's #1 rehabilitation hospital. We do a lot of our work with human subjects in motor control, human motor control, rehabilitation, and prosthetics in conjunction with the Shirley Ryan Ability Lab. So again, today I'm going to focus on some of the work we're doing in robot manipulation. And our work in tactile sensing is relatively recent, so we're still learning a lot from the people in this workshop. So thank you all for your contributions. My background is I spent a lot of years, and I still do, work on something called non-prehensile manipulation. So this is where you don't have a grasp of the object, and yet you're trying to control the motions by, in this case on the left, using vibratory motions to create programmable vector fields, or on the right here, doing different kinds of contact modes, but without ever achieving a firm grasp of the object. So a big part of it is understanding mechanics and then using your understanding of mechanics to cause motions that you can't directly control. So that's sort of where I started from, but then in the last few years, we're getting more into prehensile manipulation, grasping, which we've heard a lot about today. And on the left here is an Allegro robot hand on a Wham robot arm in our lab, doing a very simple manipulation of a Pepsi can as kind of an homage to Ken Salisbury's video from, you can do the math, that's almost 40 years ago, and the video doesn't look very much different. But part of what we're trying to do is think about how we can create sensors and use model-based approaches as far as we can, and then augment those model-based approaches with data-driven approaches. So Rob Howe gave a good introduction to some of the strengths and weaknesses of using model-based approaches. I'll talk a little bit more about that today. But basically, we're trying to figure out how to do the kinds of manipulations you see in this video, in-hand manipulation, particularly rolling, sliding contacts, using external constraints, how to do motion planning of those kinds of manipulations automatically and then control them robustly with the use of tactile sensors. So the first thing I want to point out is that compliance is required for manipulating rigid objects or making contact with rigid environments. Now, I think we all understand that, but a lot of times we get that compliance for free. in the sense that, no robot is perfectly rigid. So, even if I try to drive a robot arm through a table, it's probably not going to do it. It's going to get stuck. It's going to comply somehow. So oftentimes we get compliance for free, or it's unavoidable. It's unintentional. It just comes with the design of a system. But other times we want to design for it so that we have good control over its compliance properties. So one kind of design is in soft robots that you see. It's very popular now. It's to design robots out of elastomers or inflatable materials or other kinds of materials that can stretch and mold to the environment around them. And oftentimes these are made of elastomers or 3D printed materials that do exhibit passive compliance, but oftentimes that compliance is quite complex. It's subject to hysteresis and viscoelastic behavior and other kinds of properties that are difficult to model. And if you're going to try to learn, the behaviors of these soft materials complying with the environment, then you need a lot of data typically. So we're more interested in this talk on simply characterized compliance, and you tend to get that kind of compliance from springs or other kinds of materials that have elastic behavior but not viscoelastic behavior and little viscosity or hysteresis. You could also have passive but adjustable compliance, so things like variable compliance actuators or variable impedance actuators, where you actually use an actuator to control the passive mechanical compliance of the device. That's another possibility. And you can also have active compliance control. So this is where maybe you have a force sensor at the end effector and you're actively controlling. And that often comes with bandwidth problems as you try to control high frequency interactions. So I want to start with a simple example of in-hand manipulation, and you're probably familiar with this if you've ever used chopsticks. So often when you pick up chopsticks, they are misaligned with each other. So you can see down here the two ends of the chopsticks are not at the same location, and that makes them very difficult to use. So your first primitive in using the chopsticks are to align them. So typically you'll do this by finding a contact constraint, maybe your plate, and then you'll move your hand towards that contact constraint and the two chopsticks become aligned at their ends. And now they're much easier to use. So we're interested in how we might be able to get robots to perform this kind of in-hand manipulation using external constraints to help accomplish it. So here I'm kind of jumping right to a model for how we might think about sliding compliance. So what I've got here is a picture of a fingertip in contact with an object. For now, we're going to assume Coulomb friction. So here's the friction cone between the fingertip and the object. And now think of this fingertip. For now, just think of it as a point contact, but we can generalize to patch contacts later. It's a point contact, and it is connected to this point in space by a three-dimensional spring. So it's providing XYZ compliance. So if I want to control the motion or the forces applied at this fingertip, I can control this anchor. So this is a very simple model of thinking about stick or spring sliding compliance. So we've got spring compliance, basically a relationship between forces and displacements, and sliding compliance, which you can think of if you're using Coulomb friction, there's a nonlinear relationship between the sliding velocity and the tangential force. So you can think of this just using the simple template here where you've got a point that you can control, controlling a fingertip sliding on an object, but you can also achieve this using active compliance control, series elastic actuators, a number of other methods. But for now, we're just going to think of this as a position controlled point sprung to a fingertip. And so here's an example of a task. I've got two fingers grasping this object, so much simpler than the chopsticks. It's a two-finger grasp. And I want to re-grasp it, perhaps because I'm going to do an insertion task with it next. So here's the model. We got the two fingertips in contact with the object. Here are the two anchors that control the motion of the fingertips. And the goal is to move from the initial grasp, shown up here, to a goal grasp location where you can perform the next action. And we want to ensure quasi-static balance. So in this case, while we're readjusting the locations of the fingers on the object, we don't want the object to move. And that's going to happen because if you think of the contact here between the table and the object, you can think of friction cones here that are providing resisting forces. And so if we want to do this for arbitrary grasps and arbitrary objects with arbitrary constraints with the environment, we have to think about the forward mechanics problem, which is if I move the anchors, how do the fingers slide over the object? If I want the fingers to slide in a particular direction, how should I move the anchors? We can think of that as inverse mechanics. And then solve the motion planning and feedback control problem that would allow you to accomplish this regrasp. So I'm not going to talk much about the mechanics. Just as a simple visualization here, if you imagine you had a fingertip in contact with the object here, and this is your anchor point, if that anchor point is inside of this cone, which is basically a friction cone, if it's inside there, then that point is going to stick. If you want it to begin sliding in this direction, you have to move the anchor point to the edge of the cone, and now the fingertip will start to slide. And then if you just want it to slide in this direction, you have a choice between how you move your anchor point. So there's a specific solution, or there's a general solution and a specific solution, which says, okay, I have to have a component in this direction, but to that I can add a motion component in any orthogonal direction, and I'll still get the same sliding direction. So basically, it's a one-to-many mapping from the direction I want the finger to slide to how the anchor has to move. The only difference is what is going to be the normal force during the operation. All right, so I'm not going to talk much about motion planning, but the basic idea is if this is the position of the object over time, this is where the fingertips are, and this is where the anchors are. We want to find a motion of the object, a motion of the fingers, and a motion of the anchors that are all consistent with each other by the mechanics that I talked about earlier. And then we also want to ensure robustness. Okay. So if I map that motion planning problem, which is a general statement, onto this particular problem, it now becomes visualizable as a two-dimensional space. Basically, if both of these two fingertips are moving downward on the object, then we know the edge of the friction cone that they're acting against. And if I parameterize the locations of the fingers on the object by their height, so here's the height of finger 2, and here's the height of finger 1, then as long as the fingers are somewhere in this green area, then we're going to have quasi-static balance. So the object is not going to move while the fingers are sliding down. If we try to put the fingers in any of these gray areas, then we're going to lose quasi-static balance and the object is going to tip over during the manipulation. So the motion planning problem is basically, first we're going to move the anchors so that the fingertips are now on the edge of their friction cone, and that's what this phase 1 is. Then during phase 2, while the fingers are sliding, we just want to stay as far away from these instability boundaries as we can, while still achieving the final grasp location. Okay, so this is just a video of that happening. So at the beginning, the fingers are moving so that the friction forces lie on the edge of the friction cone, and now we can begin the sliding operation, and the fingers are just repositioning themselves on the object. So this is all assuming that we know the friction coefficient and we have a good model of the object. And of course, we can do some experiments to estimate the friction coefficient. But we have some natural stability coming from the fact that there's a non-zero contact area between the object and the table. But what we really need to make this kind of manipulation more robust is we need compliance that's well characterized. So right here in our Allegro robot, we were using active feedback control, which works okay, but the motors are highly geared and there's going to be backlash and friction and other properties. So the active feedback control of compliance is going to have some strict limitations in its capability. So I'd like to have better control or better understanding of what the compliance is between the robot and the object. I'd like to be able to detect the contact points. If you notice here, we kind of cheated. We made these fingertips cones. So really, unless we rotate the finger a lot, we know the point on the finger that's going to be in contact. And we'd like to be able to measure the contact forces, or more generally, the wrench at the contact. And we couldn't do any of those with this experiment. So this experiment, we had to calibrate well in advance and hope that our compliance control of the fingertips worked well enough to get something simple like what you see in the screen here. And ideally, we'd have these fingertips be low cost. The first attempt that we had at doing compliance control using fingertips, we used the SynTouch Biotach tactile sensors that were mentioned earlier in this workshop, and they're quite expensive and difficult to interpret and weren't really suitable for the application that we have here. So it wasn't really our intention to, but we ended up going down the road of designing our own tactile fingertip because we couldn't buy exactly what we wanted. And what we're looking for is a fingertip where there's actually compliance at the fingertip itself, and that we can control that, or at least know what it is quite precisely. We want to be able to detect the contact point. So this is an example of the fingertip. We want to be able to detect where the contact is. We want to be able to measure the forces and torques being transferred through the contacts, and we'd like it to be low cost. And this was work with my PhD students, Tito, Juan, and Jian, and my colleague, Paul Umbenhauer. Okay, so the result of this project has been the VisiFlex. Or as I give it as a subtitle, yet another optical tactile sensor, because there's a lot of them out there, and we've seen a few during this workshop earlier. So I'll tell you a little bit about what's different with ours. So again, our design goals are to have a good understanding of compliance, be able to detect the contact point, measure the wrench, and have it be low cost. So this is the idea. Here's the part that's attached to the finger. Here's the tip. And then between these two parts is a flexure. And as I mentioned earlier, we want low hysteresis, low viscosity, basically elastic behavior. In more detail, so we've got a silicone polymer that acts like the fingertip, gives us relatively high friction with the object. We have an acrylic dome, and then we have this LED board that's injecting light up into the dome. And that light is usually internally reflected, so it stays inside the dome. But when we make contact with the silicone, it makes contact with the dome. It frustrates that light. It comes back and gives a signature to the camera in the base. We also have downward pointing fiducials on this LED board, so the camera can image them directly and know what the displacement of the flexure is. And so this camera is taking images 60 times a second and telling us both how the flexure has displaced and where the contacts are on the fingertip. And so this is a picture of an actual device. So this work builds on a lot of previous work on optical tactile sensors. And also Rob Howe's group created a force sensor based on a sprung, a camera looking at a sprung fingertip. And so ours has many things in common with those, but a few different features. The two that I want to call out particularly is this sensor from a long time ago, 1992, where they used the simple, also a frustrated total internal reflection model to be able to detect contact points on an object. And what turned into the OptoForce, this force sensor that became a product. Okay, so this is an image of our what the camera sees. So these are the downward pointing LED fiducials. And as we displace the dome, we reconstruct the location of the dome by looking at how these fiducials move. And then by knowing what the spring compliance matrix looks like, then we can determine what the forces and torques are that are acting on the dome. This is just showing contact point detection. So again, reconstructed over here. And it, of course, you can get multiple contacts. And this device is not going to pick up detailed surface metrology by any means, but the point of it was to make contact or to detect where contact locations are for the kinds of manipulation that I showed earlier. So there's a flexure between the base and the tip. And in the example that I showed you earlier, it was just a simple single spring with the camera looking up inside the spring. And then, we can usually when you look up in a manual or a catalog, they'll tell you what the extension stiffness of the spring is, but we can get 6-dimensional spring stiffness and change it to a different reference frame. Here, put it in the camera reference frame, and this is the stiffness properties of this particular spring. We can design parallel flexures. So in general, we've got a 21-dimensional space of this 6x6 matrix that relates the exponential coordinates describing the motion of the fingertip, how the stiffness maps to the wrenches measured in this case at the camera frame. We've come up with several different designs, and if you want to have access to all 21 of these, you have to have at least the 21 design freedoms in your flexure. But we found the most useful flexures exhibit symmetry. So the XY stiffness and the XY rotational stiffness are the same. And then there's really only two off-axis values that are actually opposite each other. So we're going to design sensors with this kind of stiffness symmetry. It also makes the calibration simpler. So we put these sensor into a very precise motion stage. Now we're able to displace it. We know the actual location, actual displacement up to a micron and very 0.001 degrees of displacement. We have a force torque sensor up there to measure the forces and torques. And with that, we can characterize the spring properties. We can also do contact location sensing by creating this rig on the top and poking the dome and getting a precise location estimate and comparing it to the to what's reported by the sensor. We find that we get average location contact errors of less than a millimeter, repeatability less than 0.1 millimeters, and our experimentally derived stiffness matrix is fairly close to the theoretical prediction, and that allows us to get wrench sensing errors of less than 0.1 newtons and less than 50 Newton millimeters. So that is just a quick summary of where we are now with the VisiFlex. We've basically come up with a motion planning and control formulation that requires this information from a tactile sensor, where the contacts are and what the forces are that are being applied by the contact sensor. So that's why we created this fingertip. At this point, we have one of them mounted on our Allegro hand. The next three are in production, and I hope to be able to report in the near future the miniaturization of this fingertip and the kinds of manipulation, in-hand manipulation we can do with it. So I will stop there and thank my collaborators on this project.
Thank you, Kevin. Any questions from the audience? Yeah, Shay. Yeah, feel free to unmute yourself.
Thank you. Yeah, thank Kevin for the great talk. So I'm Yu. I'm an assistant professor from Purdue University. Previously, I worked with Ted Edison, so at MIT for the gel side. So I'm familiar with the technique you mentioned. We have some kind of problems for calibration the force. So I'm trying to see your comments or insight. For example, if you have contact force distribution, how did you calibrate those force? Yeah, do you have any insight on that? For example, we don't know the ground truth. Yeah.
So again, what we wanted was compliance that we understood well, just for the manipulation standpoint. But if we have that, then we can also use it for force sensing with a camera. And so we made it easy on ourselves by putting in this well-characterized flexure. And this flexure is made out of spring steel. It's not made out of a 3D printed material, which tends to have a lot of hysteresis and, requires, I think, who was mentioning, I think Rob was mentioning earlier, you don't just see the displacement now, you need to know all the displacements in the past to try to estimate what kind of forces it's bearing. So we made it out of spring steel and made the problem easy. What we can't do is if there's two contacts or a range of contacts on the fingertip, we can't tell the pressure distribution. All we can tell is the total wrench, because we're getting our wrench measurements from seeing how the entire dome displaces. Now, having said that, the silicone cap has little bumps on the bottom that kind of maintain a gap with the silicone or with the acrylic waveguide. And so when it gets pressed down, those little bumps grow in radius. And so you can actually get some local estimate of the forces, but we can't measure the local shear forces very well at all.
Thank you. Got it. Thank you.
Sure.
I think so there is a comment in our chat window. I think Oliver Brock pointed to a different tactile fingertip that's used to read Braille with acoustic tactile sensing. Oliver, I'm not sure if there's a question here, but feel free to unmute yourself if you have a question.
Now I'll ask a question. Hey, Kevin, really cool. So can you only showed kind of very pointed contact. Can you detect sort of patches and edges and things like that?
Yes. So it's just a camera, so it's seeing whatever contacts you place on the hemispherical dome. So if your object is convex and our dome is convex, you're going to see a convex patch. Right, but if your object is non-convex, then you're able to see, line contacts or other kinds of contacts. Like, for instance, if you push the fingertip into a hole, you're going to see the outline of the hole.
So do you think which of these modes do you think is going to be more relevant for your applications?
Which of what modes? Oh, the kinds of contacts we'll want to use. Yeah, that's a good question. So we've been mostly doing convex on convex, so things turn into points and patches. But obviously, if you've got a non-convex object, you can create a range of contact locations that give you both better kinematic constraint as well as greater force generation capability. But we haven't done anything more with that yet.
And do you have any idea of how to couple this with control?
Yes. Yes. So because we have a simple spring, a flexure, we're doing position control of the fingertip anchor. And then if you've got displacement measurement of the spring, which we do through the camera, we can do force control. And then the compliance, we don't really control directly. We get passively from the spring. So we can do force control, and we can do motion control when we bring in our models of rigid body mechanics, for example.
Makes a lot of sense. Thanks.
Thanks, Oliver.
There's one last question from Rob. Rob?
Hi, Kevin. Slick device, and the flexure is, of course, the key to almost any force sensor, wrench sensor. Yours is wonderfully simple. Do you have any thoughts about what would be ideal? What kind of stiffness behavior would you like? Is a diagonal matrix the goal, or are there clever things to do?
So just in this picture here, it's still projecting. We've got a simple single compression spring, but the idea is that you can just swap that part out and put a new piece in. So now if you've got a much stronger hand, you put a stiffer spring in there to be able to use the full capability before you reach saturation. So we want to make it so that the flexure is easy to swap out. It's designed modularly that way. But to your point, yes, diagonal is easiest and simplest, and that's usually the goal we go for. You're not going to get diagonal unless you're allowed to choose the reference point anywhere along the axis. So if we always choose it at the camera, we're going to have off diagonal, but just two. And we're going to try to keep not just diagonal, but have two of the elements and two more of the elements be the same on the diagonal. That gives us the most symmetric behavior of the flexure. So yeah, you have to think about how to design your flexure to achieve those. And that's ongoing work by one of my students.
Very good.
Thanks.
Thank you. So in the interest of time, let's move it. Let's thank Kevin again for the wonderful talk. And with that, we go to our final invited talk for this workshop this year. It's by Professor Jan Wissel. Jan, are you here? Awesome.
I am.
Professor Jan Wissel is an associate professor at the University of California, Santa Barbara in the Media Arts and Technology graduate program.